Welcome to the first of the QuakeCoRE seminars, monthly seminars for 2019. I'm going to be giving this seminar for those that haven't met me. My name is Brendon Bradley. I'm a professor here at the University of Canterbury and also recently transitioned to the director of QuakeCoRE. And so what I'll be talking about for the next 25 to 30 minutes as part of this seminar is associated with research that's undertaken principally within QuakeCoRE, associated with Flagship 1, which is titled Ground Motion Simulation and Validation. But the topic that I'll talk about extends ever so briefly beyond that, in particular, as the title suggests, looking at both the present and also future directions in that topic and then its implications for seismic design and assessment. So of course, to acknowledge all the other researchers at multiple institutions that are working in Flagship 1 and whose results I'm largely presenting on their behalf. Okay, so there's a couple of sort of key ideas in the context of ground motion simulation and validation. This is still showing slide 1, but I'm on slide 2, I think. Can people see slide 2?
No.
Okay, hang on, sorry, Mustafa. Okay, now maybe is this first slide and then second slide. Okay, perfect. So there's three sort of key trends that the research in Flagship 1 on ground motion simulation is building on. So the first of those key trends is the fact that we have exponentially increasing measurement data. So these two plots show, by way of example, the ground motion recordings as a function of the year in which they've been recorded. The left-hand figure is a database compiled from global events that's associated with shallow crustal earthquakes. And the y-axis in particular is plotted on a logarithmic scale. So you can see that, broadly speaking, every 10 years we have almost a 5-fold increase in the number of strong motion measurements that have been obtained. However, at the same time, the right-hand figure is highlighting that the distribution of those ground motions that have been used as a function of time is actually predominantly coming from smaller amplitude ground motions. So that right-hand figure shows that the solid black line, most of our ground motions that are increasing in these databases are small in amplitude, and therefore, in order to actually make use of them, we need better means to understand the extrapolation from small amplitude events up to the large amplitude events that we ultimately care about. The second key aspect is associated with our ability to better model the observations, and a particular aspect associated with that is the improvements in hardware, in particular high performance computing. And we see, broadly speaking, within the industry, so-called Moore's law, where we're getting a doubling a little under every 2 years, but probably more importantly, we're seeing significant improvements in the efficiency at which computing hardware has been used. And so the figure that's shown on this screen is highlighting approximately the amount of computational core hours that have been used year over year for research under the it's both QuakeCoRE and pre-QuakeCoRE, obviously prior to 2016, but work on the NESI, the National E-Science Infrastructure high performance computing platforms that's been undertaken on the topic of ground motion simulation. So again, you can see the y-axis is logarithmic, so there's quite a significant, more than doubling basically every year in the amount of computing that's been used to address these problems. The third one in particular is associated with advances in software. And this is to some degree a relatively newer trend where we're seeing significant improvements in our ability to use large amounts of data, either direct measurement data that's obtained from ground motion instruments, or more commonly and more usefully simulated data that's actually coming out of these computational calculations, and using techniques and machine learning to better understand how we can make use of these ever-increasing data sets. And so the top example is sort of a generic picture that is often used in fields like computer vision to try and understand how we can recognize images and using computers, whereas the bottom example is one schematic illustration of an example research that's been undertaken within Flagship 1, looking at how we can use large data sets of simulations to actually invert and understand what earthquake has just occurred based on the recorded strong motion measurements, and then project the distribution of ground shaking over a particular region of interest. So just to take a step back and try and make sure we're all on the same page in terms of the broader context of this problem, we really have on the left-hand side our conventional approaches of using empirical ground motion prediction methods. And simply put, in this image on the left-hand side, the black lines represent the model prediction. The solid line is the sort of average or median of that prediction. The dashed lines give an indication of the uncertainty in that prediction. And then each of the different data points there are shown. And one key thing to notice is that we have significant scatter in those observations and in our empirical model, keeping in mind that the y-axis of that scale again is logarithmic. And then in contrast, on the right-hand side, we have sort of a schematic depiction, in this case for the 22nd of February 2011 Christchurch earthquake, of what a physics-based ground motion prediction model looks like, where we're actually modeling the earthquake rupture process and then the consequent wave propagation that happens as a function of space and time. So there's some nice analogies between the empirical versus physics-based comparison of ground motion prediction, and then also the same in the context of weather prediction, where on the bottom left-hand side, the empirical equivalent for weather prediction would be to use the last 100 years, for example, of weather on the 21st of May, in order to give us a prediction for what would be the daily high and the daily low for that subsequent day in any given year. So, you know, to put that in context, if we were to predict today's weather, fortuitously, given the talk on the 22nd of February 2011, we would use the last 100 years high temperatures on the 22nd of February every year for the last 100 years, and take the average of that to predict what today's high would be. So in that context, that sounds relatively absurd compared with what we actually do today, which is shown on the bottom right-hand image, which is make use of physics-based models of the atmosphere in order to understand how our initial conditions, which is our weather conditions at a given point in time, can be used in this physics-based simulation to predict how weather evolves over the coming hours or days or even weeks. Of course, it's not just that weather scientists are substantially smarter or more intelligent than earthquake scientists. There's obviously some challenges in the earthquake-induced ground motion problem, and that's principally that the phenomena is happening below the ground surface, and therefore our ability to observe ground motion phenomena is significantly less than weather phenomena. And also the things that we care about from a ground motion perspective vary significantly over small scales and over small spaces in time. And so that's equivalent to, in a weather forecasting sense, we often talk about sort of a broad spatial scale, or so-called microzonation or microclimates. Equivalently, in the ground motion problem, we care about the very localized variation in ground shaking that exists from one part of a region to another. So on that basis of an overall sort of context of the problem, the research in Flagship 1 is structured according to this sort of overall diagram. But although there's a significant amount of information here, there's really three key aspects. On the left-hand side, we have various different themes within the scope of ground motion modeling. They collectively help us develop the models to actually undertake ground motion simulations. Once we undertake those simulations, one of the most important things is that we actually validate them using observational data. And there's a few different means by which that validation can occur. And clearly the comparison with observed data helps provide a feedback loop to then improve the underlying physical models. And then finally, once we have sufficiently validated models, we can undertake prediction in the future sense or a prospective sense for the purposes of engineering utilization. And they may be through examining particular scenario earthquakes, or more comprehensively through a probabilistic treatment of many different possible earthquakes that can occur in the future. So there's really three key ingredients associated with ground motion simulation methods that I'll describe over the next 3 slides. The first one is clearly we need a description of the earthquake source, or the rupture that actually occurs and causes consequent ground motions. And so in this slide, there's a few sort of subtleties that describe the challenges that we have in trying to describe the earthquake source. The first one is that we have what we'd refer to as fractal complexity, meaning we have complexity at all different length scales. And so that's highlighted, for example, in the upper left-hand figure from the perspective that we see variations in the amount of movement of a fault in terms of the amount of slip, but also we see it at the actual geometric level where faults are not simple planar surfaces in 3 dimensions, but they actually have a local sort of roughness to them. On the right-hand image, we can see 3 different figures that describe for a representation of the slip that happened in the 22nd of February 2011 Christchurch earthquake. The top figure, what is the variation in slip over time with the different colors indicating large through small amounts of slip. The middle panel representing what we refer to as the rise time, which is the duration over which the movement occurs at a particular point. And then the bottom panel, the rake angle, which is the direction of movement of that particular piece of the fault. And so clearly, while it might be nice to think that a fault on average moves, say 3 or 4 meters, clearly at a local scale, we see significant variations in the amount of movement, the time at which the movement occurs, and the direction in which the movement occurs. And then finally, in the bottom left, an example of the fact that earthquakes can be more complex than a single fault plane is the 2016 Kaikoura earthquake, where we clearly had multiple fault planes that ruptured to cause a large magnitude 7.8 earthquake. Once we are able to describe the earthquake sources, the next key ingredient is a model in 3 dimensions that we can actually use to undertake wave propagation in order to quantify how movement on the earthquake source then propagates toward a particular site. And this image that's shown here highlights for the Canterbury region, as you can see in the small inset figure down the bottom, a total of 5 different transects across that region, illustrating the effect of sedimentary basins and underlying rock conditions on consequent wave propagation. And so the color coding there, the cool colors, the blues indicate softer deposits, through to the red colors, which indicate stiffer deposits. And these, what we would refer to as impedance contrasts, are critical for describing the way in which waves propagate throughout a particular region. The third important ingredient is an extension of the second ingredient, but very much focused at the shallow near surface. And here we face several important difficulties, and that's that when we're trying to undertake ground motion simulation at a regional scale, which is on the order of tens or maybe even hundreds of kilometers, the variations that we see in the near surface actually have a completely different scale, maybe on the order of 1 to 10 meters. And so we have the challenge of being able to model things at that 100-kilometer scale while also having enough spatial resolution at the meters scale. And therefore, often in ground motion simulations, there's either one of 2 approaches taken, where the first one is a so-called sort of empirical VS30 based factor that's sort of added on top of the regional ground motion simulation. So the site response is not actually treated explicitly. And then the second approach, where we do explicitly model site response, is through the use of wave propagation, but now at a very localized level that's conducted subsequent to the actual regional ground motion simulation itself. Okay, so to try and illustrate those concepts, some of the obvious examples that we can look at are recent major earthquakes that have happened in the New Zealand region. And one area where New Zealand is fortunate, so to speak, in terms of the efforts toward ground motion simulation and validation, has been the large amount of significant earthquakes that have occurred in the past decade, which provide us with validation data to understand the predictive capability of these methods. So the 3 significant examples are the 2011 Christchurch earthquake, 2010 Darfield earthquake, and 2016 Kaikōura earthquake. And as you can see in this figure, those examples provide a nice full trio, because we approximately increase by 1 magnitude unit as we consider each of these 3. So 6.2, 7.1, and 7.8 magnitudes. And you can also see that we increase in the complexity of the fault rupture from a relatively simple rupture with 1 fault, although some science suggests that it may have been more than a single fault, through to the Darfield earthquake, and then of course the 2016 Kaikōura earthquake. And so one important thing in the results to show subsequently is that all of the simulations that are undertaken utilize the same methodology and the same input parameters, and the only things that vary from one simulation to another are the different source model in order to represent different earthquakes, and then of course the different geographic location in which the simulation is undertaken. And obviously it's critical there that we are validating models with past data in exactly the same way that we would apply those models to predict future events. So let's just look at one example for the 2016 Kaikoura earthquake, and this is a visualization which shows the variation in the ground motion intensity occurring as a function of time. The particular colors that are highlighted tell us the strength of the ground shaking, in this case in terms of peak ground velocity, as shown in the bottom right-hand corner. And then in addition to that, in the upper left-hand corner is several numerical models of buildings that are located in the Wellington region. Obviously, those buildings have different heights and different vibration properties. And then this is some CCTV footage of a call center located in the Wellington region. And we've coupled these various things together so that they're phased in time. And so you can see one of the significant things about ground motion simulations is our ability to understand that evolution in time. It provides us with an actual acceleration versus time measurement, as opposed to empirical models that just give us a measurement of the maximum shaking. And then as one other corollary from a outreach perspective, is we see significant value in the ability to visualize what's actually happening. Because these are past earthquakes, we obviously have observed ground motions as well. This figure is showing the one of the three components of ground motions recorded at strong motion stations throughout New Zealand through the GeoNet program. And we can obviously compare those observed ground motions shown here in black with simulated ground motions that are shown in red. The three different columns in this figure are illustrating the north, south, east, west, and vertical components. And then horizontally, they're grouped into three different sort of categories: those in the near fault region, those in the epicentral region in particular, located down in North Canterbury, and then the bottom two images shown for the Wellington region. And of course, we can look at these figures and see that clearly we don't match the observations wiggle for wiggle per se, but when we look at the overall amplitude, frequency, content, and duration, we're clearly picking up some of the key salient features in the observations. We can compare predictions and observations in a different form that's particularly useful from an engineering perspective, which is using so-called ground motion intensity measures. So these four images represent four different intensity measures. The upper left-hand plot is the so-called peak ground acceleration. And then from the upper right down to the bottom right, we have three different measures of response spectra at periods of 0.2 seconds, 3 seconds, and 10 seconds. And then for each of the plots, the x-axis is a function of distance from the earthquake source. The green points represent the observed ground motion amplitudes, the red points the simulated ones, and then for reference, the black line is using one of our simplified empirical models. So when we look at those four figures, there's a couple of sort of high-level trends that stand out that are important. In the top two figures, the top row, we see that actually the green observations tend to reduce in amplitude with distance more quickly than the empirical model shown in black. And actually the red predictions of the physics-based model are more consistent with those observations than the empirical model. And then if we look at the bottom row, so the response spectra for 3 seconds or 10 seconds, we see that at distances of around 100 kilometers, plus or minus sort of a factor of 2, there's a significant variation in the ground motion amplitude, so the y-axis values, that spans more than an order of magnitude, even though the variation in distance is particularly small. Our empirical model doesn't catch any of that large variation in amplitude, whereas our physics-based simulations do. And the principal reason for that variation is the directivity associated with that particular earthquake, where we generally had we generally had rupture from the southern portion up into the northern area, and so that produced stronger than average ground motions north of the main near fault region and weaker than average ground motions south of that region. So we're able to pick up some of those important physical factors through the use of these simulations, whereas our empirical models generally don't contain such features. While those three events, the two significant Canterbury earthquakes and then the 2016 Kaikōura earthquake, are particularly useful because of their large damaging nature. In order to really develop predictive confidence in these simulations, we need to use significantly more events. And so here's a few examples of some other studies that are either previously undertaken or ongoing. Where in the Canterbury region, we've looked at about 150 earthquakes of smaller magnitude that have been recorded. And then also in the Wellington region, some ongoing work has been looking at approximately 200 earthquakes. And that's been from the perspective of trying to understand how significant the observations in Wellington from the 2016 Kaikōura earthquake are relative to what we've seen in the Wellington region in the past. And these are all part of a more broad study where we're examining about on the order of 2,000 earthquakes above magnitude 3.5 that have been recorded since the GeoNet program commenced in 2003. And this is all focused on developing a comprehensive understanding of the predictive capabilities of these simulations. Without getting into the nitty-gritty associated with the validation results themselves, already we see that the comparison between empirical predictions and simulation predictions of historical events are either comparable. In some cases, empirical models are slightly outperforming the simulations. In other cases, the simulations outperform the empirical predictions. But as I'll talk about in a few slides, we're already seeing some substantial improvements in our simulations. And so we expect that over time, it'll become relatively self-evident that we achieve significantly improved predictions with those simulations. A couple of illustrations of where some automated tools are becoming particularly useful is that as we go to these large magnitude earthquakes, we have thousands or tens of thousands of ground motions in which we need to make use of. And so it actually becomes significantly onerous to look at each of these ground motions individually and classify whether the recording is high quality or whether there's significant noise in the record that makes it a poor quality recording to use. And so we've been using machine learning tools in order to automatically classify some ground motion recordings. And then of course, in order to actually pass this validation information and the underlying simulation tools into practice, we need guidance for both the validation and the utilization. And so this was some work that was undertaken in 2017 in order to demarcate simulations that are appropriate for use in some applications versus those that haven't gone through sufficient rigor to be useful in practice at this stage. Clearly, when we think about future events, there's no deterministic statements that we can make, and therefore we need to consider things from a probabilistic perspective. And this particular figure is illustrating approximately 500 major mapped faults that are located in the New Zealand region. This is part of the sort of national seismic hazard model consensus model in 2010. And if we take a look at just what one of these representations would look like, this is for a simulation of the for a large magnitude earthquake on the Hope Fault, then this is essentially what we're undertaking for each and every one of these major earthquakes that could cause significant ground shaking in the future. So we have a representation of the earthquake source, in this case the Hope Fault. It spans from approximately where Arthur's Pass is located in the Alpine region through to the Kaikoura coastline on the eastern extent. And in this particular example, we consider the possibility that the rupture initiates near the middle of the fault and then obviously ruptures in both directions along the fault. And here again, you're seeing the variation in the ground motion amplitude as a function of time. And one of the most important things that I didn't highlight in the previous animation is the role in which that local geophysical properties of the Earth's crust play in terms of amplifying or attenuating the shaking. So in this particular animation, there's several regions where we do have sedimentary basins, and the reverberation in those basins leads to ground motions that are both stronger and also tend to last longer in duration than what we see in the surrounding region. And so for each and every one of the ground motions, each and every one of the potential future earthquakes, we undertake physics-based simulations such as these, and then we need to combine those into a model of ground shaking. Okay, because there are significant uncertainties in what may happen in the future for each potential fault, we need to consider a range of different possibilities for how that rupture may occur. And so in the most simple sense, we can consider different locations where the rupture starts. That example for the Hope Fault, consider the hypercenter located in the middle of the fault, halfway along the strike direction. It could start at the far western end, it could start at the far eastern end, and so we consider a range of different possibilities in that regard. And then also there's the potential in our representation of the 3D crust. There's significant uncertainties in some of the modeling assumptions there as well, and we can represent that through different assumptions in the same manner. Once we undertake each of these simulations, we want to aggregate them all together, and so we store them on a grid, in this case of little under 30,000 locations throughout New Zealand that you can see here, higher spatial density in regions that we care about where there's significantly more population. And then that allows us to undertake these simulations. We make use of a software workflow that's sort of schematically illustrated here, and use the NESI computing resources, which are located in Wellington and Auckland. And so there's several different products that we can produce. For example, these are one conventional type of depiction, which is the so-called hazard map. And what we're looking at here is in terms of peak ground velocity at a probability of 2% likelihood of exceedance in 50 years, 3 different depictions. The far left-hand side is the result that we get in terms of using the simulation-based ground motion prediction. The middle result is using our conventional empirical models, and then the right-hand image is the ratio of the two. So you see that generally speaking, they do follow similar trends. You know, that's clearly you get significantly more earthquakes along the alpine regions of New Zealand and the South Island and the east coast of the North Island, and therefore both models predict the highest ground motion hazard in those regions. But there are more subtle local variations that you can see looking at that right-hand plot. And I think one of the key ideas to keep in mind when comparing these different models is recognizing that the empirical models are based on observations, and therefore they inherently don't have bias in them, but they do have a significant lack of precision. So what we hope to obtain using these more advanced physics-based methods is improved prediction precision, and that translates to being able to more clearly understand how the spatial variation in ground motion changes in different parts of New Zealand. So now sort of turning back to another application of machine learning in the use of these simulations is that we have many simulations. The examples that I was showing you for that hazard calculation are using a little under 15,000 ground motion simulations. We also have simulations of past events, and we can use those as so-called training data to essentially develop algorithms, in this case machine learning algorithms, that allow us to read in a set of observed ground motions at strong motion stations, classify what earthquakes we think just occurred, and then on the basis of those earthquakes that we classify, what the predicted ground motion might look like. So if you envisage immediately an earthquake occurs and we record ground shaking at say 50 instruments, we plug those recorded ground motion amplitudes into this machine learning algorithm, and it spits us out a prediction of which faults just ruptured and what the consequent ground shaking is. And so this is quite a different approach than the conventional means by which we understand near real-time prediction, which is we observe the ground motion recordings at strong motion instruments, we solve a geophysical inverse problem to try and understand what earthquake just occurred, and then we use empirical ground motion models to predict that shaking. So this is quite a sort of tangential approach, which I think will complement the existing approaches quite well and probably ultimately provide a superior prediction as the amount of training data increases. At a very high level, it's useful to keep in mind how the predictive capability of these empirical and simulation methods are changing over time. And so the data that I'm showing here is from Fleur Strauser and colleagues in 2009, where they were looking at prediction uncertainty as a function of the year in which different empirical models were published. And we see that actually we've definitely hit the point of diminishing return in our ability for these empirical methods to provide improved predictive capability over time. And in contrast, what we're seeing with physics-based simulation methods is now a drastic reduction in their prediction uncertainty. And that's really happening as a confluence of those 3 technologies I mentioned before: improved data, improved computation, and then also machine learning methods. And we're now starting to reach this crossover point where simulation-based methods are outperforming empirical methods. One of the important things to highlight in this sort of schematic depiction is the use of sort of a shaded region for each of the prediction methods. And that's not to imply, that is to imply that the crossover point when these simulation methods outperform empirical methods is actually a function of the particular region and also the particular ground motion features that are of interest. And it should be relatively intuitive to understand that because our models are based on physics, if we have good models of the Earth's crust in one region but not good models in another region, then clearly we'd expect these physical models to perform well in the areas where we have those good crustal models and vice versa. We can then make use of these ground motion simulation tools to extend beyond ground motion to also look at geohazards. And so here's an example looking at both liquefaction and landslides susceptibility over New Zealand. And then the application in conjunction with researchers in the Resilience Challenge and also part of the QuakeCoRE Special Project in that regard on distributed infrastructure is understanding how these ground motion hazards vary across the footprint of New Zealand and the various different spatially distributed infrastructure networks that we have. And so the research results shown in the bottom right-hand side provide us with an understanding of that susceptibility of ground motion and these geohazards to those distributed infrastructure networks. So with that, I'll finish and happy to take any questions, and thanks in advance for your attention. So obviously, if you're on the Zoom call, just feel free to unmute yourself and ask questions at will. Or people in the room in Canterbury, obviously. Any questions? Eerie silence. Okay. Brendon.
Just from an outreach perspective, do you see in the future that this will be available for the public to see you and play with and interactive content?
Yeah, so the question was associated with outreach in terms of the ability to make use of particularly the sort of visualizations and maybe the final products for the purposes of public information, I guess. And so definitely the answer is yes, and it's always a question of how close to present sort of the latest research results in a public setting versus presenting things that are ever so slightly outdated, but now you're more confident in the results, and also making sure we don't overwhelm the layperson with, 15,000 different possible earthquakes that could occur in the future. But I think one of the key benefits of simulation-based methods is you can visualize them, and they do show how things vary with time. So several of us that have made use of these simulations for outreach, particularly through Project AF8 with the Alpine Fault, is how many people don't understand things as simple as earthquakes don't all rupture the fault in an instant. That it starts at a point and it moves at about 3 kilometers a second with time. And so an earthquake that's several hundred kilometers long actually takes minutes to rupture. So I think there's some really powerful outreach improvements that we can make by using these methods, and definitely researchers within Flagship 1 are trying to enable that to happen with their results.
Do you see a difference in your ability to predict peak type parameters versus, say, more integral or energy-based parameters that duration?
Yeah, so thanks, Steve. The question was associated with prediction of different measures of ground shaking, whether they're measures of peak shaking, peak acceleration, or spectral acceleration, or more cumulative measures of ground shaking. So we do see a bit of a difference. Currently, I would say on average, we're better at predicting the peak measures, albeit that the improvements that we've been able to make to correct some of the initially poorer predictions for cumulative measures were actually quite straightforward. So it's often the case that in developing these simulation tools, certain features have been of higher interest, and peak measures being the obvious example of that, and therefore some of the original methodologies that we were using about a year ago, we didn't actually do very well at predicting the duration of shaking, but it was actually very easy to make the necessary modifications to do that, and now we see improved predictions in that regard. So I think one of the benefits of the simulation-based methods is the sort of causality of the problem. Makes it very easy to understand how changes in inputs create consequent changes in outputs. One of the things that we've struggled with as a community with empirical models is all of those features are coupled together, and therefore it's very hard to untangle one physical feature from another. So yeah. Okay, if there are no other questions, thanks to all the people that have attended the seminar, and a reminder that these seminars are posted on the QuakeCoRE YouTube page, therefore you can repost them on any other third-party pages at your leisure. And also we're having these seminars once a month, and always happy to take volunteers for future months to present their research results. So thanks.
Brendon, maybe I could get a question in before you sign off.
Yeah, certainly, David, go for it.
Yep. Are you doing much on the Hikurangi subduction margin?
It's something that we're sort of commencing validation is a critical component in that regard. One of the main challenges with subduction zone simulations is that our validation data in a New Zealand context is relatively sparse compared with shallow crustal events. And so to some extent, our focus has been more about trying to reach critical mass, focusing on shallow crustal events, and then slowly pivot across to subduction zone and subduction interface events. So that is a big focus for 2019, but I think there are some significant challenges there in terms of the validation of simulations, but it's a good point. Okay, thank you everyone. Have a good day.